So if we look at the truth table of a JK flip-flop, JK and then clock, and then this is Q. So when both are 0 and clock comes, the output is no change. If 0, 1 and clock comes, then output will become 0. If 1, 0 and clock comes, output will become 1, and both inputs are 1, clock comes, output will toggle. So that's how a JK flip-flop goes. Now with these two combination input combined, we can have a D flip-flop, and with these two we can have a T flip-flop, and that we can have very easily. So J and K here, if they are tied together, because both inputs are the same, it becomes a T flip-flop. And J and K here, if they are connected via an inverter, a NOT gate, and this becomes the input, if we get a D flip-flop. So we will have clock always. I don't know, clock should be shown here. So that's clock, and this is output here, so output there. So J and K, T and D flip-flops. So if I want to make a counter using D flip-flop, I have done before, but I will again talk about it slowly. So here we just want to make a 2-bit gray code counter. So 0 0 gray code, 0 1 1 0 and 0 0 1 1, that's 2-bit gray code. We want to make it make a 2-bit, sorry, we want to make an up counter using D flip-flop here. So it should count like this, from here to here, from here to here, and then from here to here. Now when we are using D flip-flop, we will identify this as present state, and here we will write the next state for each of the present states. So this is 0 0, when if we write here Q1 and Q0 and D1 and D0. So when Q1 and Q0 both are 0, the next state for counting up will be 0 1, because it's from here, so that will go here as the next state. Similarly, when 0 1, Q1 and Q0 are 0 and 1, the next state is 1 1, as we can see here, so here it will be 1 1. Similarly, when it's 1 1, it will be 1 0, and when 1 0, it will go back here, so the next state is 0 0. Once we have that, since we have only 2 bits here, we don't have to use a K-map. We can just write directly looking at the truth table. So if we want to write the expression for D1, so first I will draw the flip-flops. This is D1 and this is Q1, this is D0 and this is Q0, and these two are clocks here. So for this arrangement, with making a counter using D flip-flop, the clock will be synchronous, connected to system clock, and we will have to figure out what will be the D1 and D0 inputs are. So we will figure out that by looking at the truth table. So D1 is 0, D1 is 1 here. I will use a different color, 1 here and 1 here, and when we look here, we can see that in this case Q0 is 1 in both cases, and when D1 is 0, so D1 is basically following Q0, that's what's happening. So we can just connect Q0 to D1 like that. Similarly for D0, these two 0, and we can, when we look here, we can see that Q1 is 0 in both cases. So these two are 1, this is 0, but when these two are 0, Q1 is 1 in both cases. So what is happening is Q1 bar is D0 is following basically Q1 bar, it's inverted, so Q1 bar is here, this will be Q0 bar, so this Q1 bar can be connected to D0. So this way we can have a 2-bit gray code up counter using D flip-flops. Now this to make the counter using T flip-flop may not be very convenient. I will not go into that. I will make another video how to, when we want to make a up counter and make an up counter or a down counter using T flip-flop, we have to apply different strategy. Like for D flip-flop, what we have had to do is we had to write a present state and next state, and then here we looked at the next state D inputs. These are actually D inputs, because whatever is here, this is next state, but with clock the next state goes to the output. So that's how it works, D flip-flop. D flip-flop doesn't work that way, so we have to adopt a different strategy. So that's what we should do whenever we are using D flip-flop. So I'm just restricting this video into D flip-flop, discussion about D flip-flop.